Okay, guys, welcome. Today we're going to talk about counting and probability. Now, the first type of counting that we're going to talk about is when you have arrangements with repetition. Now, if you make R different selections from a group of N choices, then you have a total of N times N times N, where you have R of these N's, right? Or N to the R power. And that's how many different arrangements are possible. Let's take a look at an example that would showcase that. Now in part A, we want to know how many 7-symbol license plates are possible if both numerals and uppercase letters can be used in any order. Now you have 7 slots, right? So 7 slots. Now if you can use numerals, that's 10 different digits, right? You could use 1 through 9 and 0. And you can also use any uppercase letters, so that's another 26 possible choices. So then for each slot, you have 36 possible characters to choose from, right? So if for each slot you're choosing 36 things, and you're doing that 7 times, then you have 36 to the 7 possible choices. And we're just going to leave it in this form because if you put this in your calculator, you're going to get some huge number. All right, so a lot of times we just prefer to leave it in this way. Now in part B, we want to know how many 6-character passwords can be made by combining lowercase letters, uppercase letters, numerals, and the characters for the @ sign, cash sign, and the and sign, right? So we have 6 slots now. And if we can use lowercase letters, that's 26. If we want to use uppercase letters, that's also 26. And then we have 10 numerals that we can use. And then, of course, the 3 extra symbols. That's going to give us a total of, let's see, so we get a 52, 62, and a 65. So in each slot, we have 65 choices. And then, of course, we multiply them together. So we're going to get 65 to the 5th power, which, again, is going to be some huge number. So we'll just leave it in this form. Okay. Now, the next type of counting principle that we're going to deal with is what is called permutations. Now, when we deal with permutations, whenever all selections come from a single group of items, and you have that no item may be selected more than once, and the order of the arrangement matters, right? So for example, ABC would be different from BCA. Now, if every member of the group is selected in each possible permutation, then the total number of permutations possible with a group of n items would be n factorial, right? And of course, n factorial just means that we take every number starting from n and we subtract it by 1, and we continue subtracting by 1 and multiplying these numbers together until we get down to 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1, which I guess would be 120, right? All right, so that's what we mean when we say factorial. And that looks like just a duplicate slide. So for example, a middle school's principal needs to schedule 6 different classes: algebra, English, history, Spanish, science, and gym in 6 different time periods. How many different class schedules are possible? Well, I think it helps to see it sort of illustrated this way. All right, so we have 6 different periods. This is first period, second, third, fourth, fifth, and sixth. Now, in the first period, you have 6 classes to choose from. You can pick any one of those 6. Now, in the second slot, you've already picked class for first period, so now you only have 5 to choose from. And then you have 4, and then 3, and then 2, and then 1. So now if you multiply these together, you're going to get 6 times 4 times 3 times 2 times 1, which of course is 6 factorial, which if you multiply out, you'll find will be 720. right? So you can either leave it as 6 factorial, or if you really want to, you could write out 720 also. Okay. Now, we can also look at permutations when we select selections from a single group of items and we only want to select some of them, right? In this last example, we had to select all of them, so we just use the factorial. Now, again, you're going to have a permutation when all selections are coming from one group of items. No item may be taken more than once, and the order of the arrangement matters. So now if you choose R things from a group of N items, then the total number of permutations is this sort of like an N and then a P and then an R, right? So it's sort of the subscript with the NPR. And then that's equal to N factorial over N minus R factorial, right? And we say that NPR is read as the number of permutations of N items taken R at a time. So in example 3, we have that a city has 12 candidates running for 3 leadership positions. The top vote getter will become the mayor, the second vote getter will become the deputy mayor, and the third vote getter will become the treasurer. Now, how many outcomes are possible for the 3 leadership positions? Well, we can think of this either in slot form, or we'll think of it as permutation form. Now, in slot form, you have 12 possibilities for the mayor. Once you have a mayor, you then have 11 possibilities for the deputy mayor. And then once you have the first 2 chosen, you then have 10 for the treasurer. So this would be 12 times 11 times 10, which would be 1210. Now, if you think of this in terms of a permutation, we want to think of, since we have that, how many outcomes are possible for the 3 leadership positions, note that the order does matter here, right? Because if you have A, B, C as your top 3 vote getters, that's different from C, A, B as your top 3 vote getters. So this means that I have 12 permutations from which to select 3. And of course, the formula for this is to take 12 factorial and divide this by 12 minus 3 factorial, which is 12 factorial over 9 factorial. And one way that you can think of this might be a pain to sort of simplify, but think of 12 factorial as 12 times 11 times 10 times 9 factorial. Well, now your 9 factorials can cancel and you're left exactly with what we calculated before, right? So that's another way that we can sort of handle this problem. Now, in the next example, we have that a Little League manager has 15 children on her team. We want to know how many ways can she form a 9-player batting order. Now, since we have a 9-player batting order, the order will again matter here. So this means we're dealing with a permutation. Now, since we have 15 children to choose from and we want to select 9 of them, this would be 15, P, and then 9. So we're going to have a 15 factorial over a 15 minus 9 factorial. So this will be 15 factorial over 6 factorial. And this will be quite a large number, so we'll just leave it in factorial form. Okay. Now, what if the order doesn't matter? Now, if the order doesn't matter, now you're looking into the idea of combinations. Now, combinations occur whenever all selections come from a single group of items and no item may be selected more than once, and the order of the arrangement, again, does not matter. So A, B, C, D is considered the same as D, C, B, A. Now, if we make R selections from a group of N items, then the number of possible combinations is NCR, and then we just modify our permutation formula by this extra R factorial in the bottom. Now, most of the time, I will write this in the form where we have a parenthesis and then N over an R. And I will usually use this, instead of saying the number of combinations of N items taken R at a time, I usually say N choose R. Right? And again, I'll usually use this format to present the answer. All right, but it just means this right here, n factorial over n minus r factorial times r factorial. Now, in this next example, we want to suppose that you select 3 different flavors of ice cream in a shop that carries 12 flavors. We want to know how many flavor combinations are possible. Well, think about it. If you get here, if you get chocolate, mint, and vanilla, or something like that, that's still the same as mint, vanilla, and chocolate, right? So in this case, the order does not matter. Right, and we're excluding the fact that maybe you want to finish off with mint because that's your favorite or whatever. We're going to assume here that the order does not matter, so that tells us that we're dealing with a combination. So now if we have 12 flavors and we're choosing 3 of them, this is 12 choose 3, which we would find by doing 12 factorial over 12 minus 3 factorial, and then multiply by an additional 3 factorial down here. So we're going to get a 12 factorial over 9 factorial times 3 factorial, right? So usually any of these 3 presentations of the answer would be fine, right? Because they all mean the same thing. Okay. Now, in the next example, we have that how many different 5-card poker hands can be dealt from a standard deck of 52 cards. And then we also want to comment on what is the probability of one particular hand, such as a royal flush of hearts. Okay. Now, the idea here is that you have 52 cards in a deck. And again, the order does not matter, right? If you have 2, 3, 4, 5, 6, that's the same as 6, 5, 4, 3, 2, right? So the order does not matter. So again, that tells us that we're doing a combination, right? So the number of ways that we can do this is 52 choose 5. So this is 52 factorial over 52 minus 5, or 47 factorial, and then times an additional 5 factorial, right? Now, if you were to actually calculate this out, I have the answer right here, you're going to get that this number is 2,598,960. Let me just make sure I got that right. 2,598,960. Yep. So those are the total possible hands that you could have, right? Now, if you want the probability of one particular hand, then the probability of, say, a royal flush of hearts, well, there's only one royal flush of hearts, right? And divided by the total number of possible hands is divided by this 2 million number, right? So if you were to calculate this, you're going to have, right, a very small chance. So it's going to be 1 in almost 2.6 million, right? Which would be an extremely small number even on the calculator. All right, so we'll just even leave it like that. Okay, but that's the idea. Okay, now in this next example, suppose you play a lottery in which the winner is chosen by 6 balls at random from a drum containing 52 numbered balls. What is the probability that your 6 numbers will match the 6 winning numbers? Well, this is very similar to the problem we just did. So the total possibilities would be, we have 52, choose 6, right? And I should be clear here that for this lottery, the order doesn't matter. Okay, so it's 52 choose 6, which would of course be 52 factorial over 46 factorial times 6 factorial. So if we were to calculate this number, we're going to find that we get a 20,358,520. right? So of course the probability that your 6 numbers would match this would be 1 out of 20,358,520 that the numbers match. And numbers like this are why you will never catch a mathematician playing the lottery, right? Because this is, of course, not good odds at all. Okay, now we're going to close out this video with a pretty interesting problem. So we're going to suppose that there are 25 students in your class, and we want to find each of the probabilities. So we're going to assume that there are 365 days in a year, and we're also going to assume that any birthday is equally likely. Okay, now in part A, we want to find the probability that at least one person in the class has the same birthday as you. And in part B, we want to find the probability that some pair of students in the class of 25 shares the same birthday. All right, and we'll compare this to result from part A. Now, in part A, I wrote this out so I didn't have to mess with the calculator here because you're going to get some gross numbers here. But the probability of you having the same birthday as somebody is 1 out of 365, right? So we're going to use the at least once rule. So of course, the at least once rule says that if you want the probability of at least one student sharing your birthday, you do the probability, 1 minus the probability that no one has your birthday. And since this is the same for each student and you have independent events here, we could take the probability that one student has a different birthday and raise that to the 24th power. So of course this would be 1 minus 364 over 365 to the 24, which comes out to about 1 minus 0.0936, which gives you a 0.064. So this tells you that you have about a 6% chance to share a birthday with somebody in a class of 25 students. Now, part B is interesting because now we no longer care about your particular birthday. Now it's, do any pair of students share the same birthday? Okay, so this is still an at least one problem, right? Because we want the probability that at least one pair shares the same birthday. So we want to take 1 minus the probability that no one shares a birthday. Now, if we just pick one student at random, we can then calculate what's the probability that everybody has a different birthday. Now, the first student will have a birthday on one of the possible 365 days. Now, if we take that into consideration, then the second student will have a different birthday with the probability 364 over 365. Now, the third student has to have a different birthday than not only the first student, but also the second student. So now we're down to 363 choices out of 365. And of course, we're going to continue to do this for the 4th student, 5th student, all the way up to the 25th student. And if we do that, that will leave you 341 days to choose from out of 365. Well, now the probability that no one has the same birthday is all of these numbers multiplied together. So if we multiply all these numbers together, that's going to come out to be a 0.431. And that's the probability that there's no shared birthdays. So of course, to get the probability of at least one pair sharing a birthday, it's 1 minus this number, which gives us 0.569. So that tells you that there's, in a class of 25 students, almost a 57% chance that 2 students share the same birthday. Which is a pretty remarkable coincidence because most people would conjecture that it's actually much lower than this, right? So in part A, we found that probability of you having the same birthday with somebody is 6%. And in part B, the probability of any pair of students sharing the same birthday is almost 57%. So what this shows is that particular coincidences maybe by themselves are not lucky, but if we're looking for any type of coincidence or we sort of broaden what we're looking for, we can increase the probability by a lot. All right, so that concludes this video on counting and probability. I hope you enjoyed, and I will see you next time.